Okay, so the rate at which the body moves energy, loses energy is going, so this is the cross-section times the energy loss. Then we have to multiply by the number density of stars times the velocity to get the flux of stars that are hitting the bigger one. And so I can write this as minus g squared mt squared times the density of stars over the velocity of the fast-moving particle. So that's the rate at which this fast-moving particle loses kinetic energy to the surrounding stars. And this process is called dynamical friction. And you can read all about it. Of course, it depends in detail on what this velocity is and whether this is a Gaussian or some other velocity dispersion. And if you assume that it's a Gaussian and put numbers in here, there's a factor of 0.34, which is differences of Earths and so on, but this is the general idea. And I should also mention that it's Coulomb effect, so it's long range, so there's a logarithm of the Coulomb factor here, because the very distant encounters remove just as much energy as the 90-degree encounters that I considered here. So there's the log of the maximum scale to this 90-degree scale that appears. And by Fermi's rule, all logs are 10, except in this case they're usually about 5. But so within an order of magnitude. Okay, so you can now see that these two stars, which are orbiting each other, sorry, not the two stars, the two centers of the nuclei of the galaxy that are orbiting each other are going to be losing energy to their halos in the background of stars, and so they'll inexorably spiral together. In the time scale to merge will essentially be if we give each one of these a mass m and a velocity v, their relative orbital velocity will correspond to an energy of order mv squared, and then we want to divide that by the rate at which they're losing energy to their surrounding stars. So you see we'll divide by this expression, so we'll get an mv cubed divided by g squared m squared rho star r log lambda. So one of the m's goes out. And there is our magic expression for the time scale to merge by dynamical friction. So if you put in some numbers, if you say that these are like 10 to the 10 solar mass central kiloparsecs of galaxies orbiting each other at a few hundred kilometers a second, you'll see that this time scale comes out to be of order 10 to the 8th or 10 to the 9 years. So it's short compared to the age of the universe to merge. Okay, so now the two central concentrations of stars have merged. And now we can ask what happens when we've got close enough that the two black holes, which are inside these concentrations of stars, which are merging by dynamical friction, have got close enough to each other that the black holes are beginning, rather than orbiting the stars in the galaxy, they've got close enough to each other that they're in this region less than our black dot, where they're actually dominating the dynamics, and therefore they're mainly orbiting each other rather than orbiting the potential defined by all the stars in the galaxy. So the second stage is the so-called hard binary black hole, when the separation sort of R1 minus R2, the two black holes, is less than this black R black dot. So the black holes orbit each other, not the stars. Okay, well, now it's a much simpler problem, you might think. Now what I just have is I can think of this as two black holes which are orbiting each other center of mass in a Keplerian orbit. And then there are a whole bunch of little stars in the surrounding galaxy, which occasionally zip in near the black holes. And what do you think happens to a star? Which I have two black holes which are orbiting each other, now with velocities, orbital velocities, which are larger than the typical velocity dispersion of these stars. So these little stars are sort of dropping into the black holes on parabolic orbits. Anybody know what happens? Is there a stable solution to the general three-body problem?
One of the stars get adjusted.
So the typical thing that happens is the same thing that happened to the Pioneer spacecraft. Sun, Jupiter, Pioneer spacecraft. Okay, so what you carefully arrange is that I arrange my little Pioneer spacecraft to, let's say, have an encounter which is especially close to one of these two black holes. And that doesn't require a lot of work. It just means the general encounter will be closer to one than the other in general, so that's a generic case. So let's just suppose it's especially close to this one. So these two black holes are orbiting each other with a orbital velocity, remember, which is large compared to sigma. So the orbital is much larger than sigma, and so this comes in with some velocity sigma at infinity, but by the time it's close to the black hole, it's moving much faster. Now, in the general case, this little black hole, this little incoming star will get slung around and its direction of motion will be reversed. But now look at that from the point of view of this big black hole. Okay? The big black hole sees a little star coming in and it goes out with the same velocity. And that means in the lab frame that this little star is going out with a velocity which is something like infinity, which is something like sigma plus twice this orbital velocity. That was much bigger than sigma. So that means this little star is ejected from the galaxy. And that's the general thing that happens is these stars are ejected they're ejected from the galaxy. So now I wait for another star to get in. It gets ejected. And the beginning of this phase, the mass in stars is comparable to the mass in black holes. That was the definition of the beginning of this phase. So in the first phase, I eject all of the stars that are in the neighborhood of the black hole, and the energy that I liberate in doing that is enough to shrink the orbits of the black holes by a factor of a few. And the reason it's a factor of a few rather than a factor of 2 is that the black holes are ejecting the stars with velocities that are larger than sigma, but the masses were comparable. So I shrink the orbit by a factor of a few. Now there are no more stars near the black hole. So now I can't lose any more energy, right? Kicked out all the stars and the black holes are orbiting in vacuum, so there's nothing left. Well, at this point, the typical radiation timescale for gravitational radiation is like 10 to the 14 years. So gravitational radiation is not going to solve the problem. But then you remember that there are a lot of stars in the galaxy, they're just not very close to the black holes. So perhaps I could use the stars that are happily on circular orbits over here. Well, there are two possibilities. Either those stars were on orbits which happen to be aimed quite accurately at this binary black hole, so I just wait for an orbital period and I eject them. And that happens in one orbital period. All those stars on radial orbits get ejected. And now I have to ask, so I eject not only all the stars near the black holes, but I eject all the stars in the galaxy which are on radial orbits from much larger distances that were aimed at the black holes. So now I've gotten rid of everything that's getting near the black holes. So now I have to wait for something to scatter stars back onto these orbits if I want to keep shrinking the orbit. And the two processes which can do that is, of course, one of these stars this star might have initially been on a circular orbit, and this star might have been on another circular orbit, and they might have met each other in a two-body gravitational encounter and deflected each other's orbits by of order 45 or 90 degrees with this cross-section, except put M star here instead of MT, same cross-section. And in general, they'll deflect each other onto some random orbit, but very occasionally, they'll deflect each other onto an orbit which is aimed close enough to this binary that it will have a strong interaction and be ejected. So I could wait for a relaxation time to repopulate this so-called loss cone. And the loss cone consists of those stars whose orbits are aimed sufficiently precisely that they'll get within the sphere of influence of these two black holes. And if you imagine that the semi-major axis of the two black holes is A, then the lost cone consists of stars whose orbits will take them to a pericentric distance less than A. So that corresponds to a specific angular momentum, which is like square root of G, let's call M12, is the total mass in black holes, M1 plus M2. That's GM12 times A. So that's the angular momentum, that's the relative velocity that it will have near a pericenter, and that must be equal to the typical velocity dispersion out here times the radius where they're moving with radius r, velocity dispersion sigma. And of course I have, in order to make this true, that has to be an angular velocity that's aimed almost precisely this way. So there's an angle theta, which is the angle that the velocity has to be aimed compared to the radial direction in order that the angular momentum, which is conserved, be small enough that it has this pericenter value. So the angle of the lost cone, which is a cone in velocity space at some radius r, the opening angle of the lost cone is like square root of G M12A over sigma r. So as you get to larger and larger distances, this lost cone is getting narrower and narrower. It's a smaller fraction of the stars. And so in order to repopulate the stars which are going to get kicked out, I have to ask how long does it take for two-body relaxation over there to scatter stars from outside, whose velocity vectors are initially outside the lost cone, into the lost cone. Okay, well, I won't take you through the gory details of doing that calculation, but I'll tell you the result. And the result is that for black holes, which are, if you take in the observational correlations of the density of stars as a function of radius in the galaxies, the massive galaxies don't have very many stars at large radii in their cores. And so it turns out that that relaxation time is much longer than the Hubble time. And it appears that if that's everything that's going on, you'll never be able to merge the black holes in the Hubble time. You can never get them close enough that the gravitational radiation lifetime is less than the Hubble time. However, in lower mass galaxies, where the mass of the black hole is less than about 2 × 10⁶ solar masses, it's just about possible by that process alone, namely two bodies scattering, filling the lost cone, and providing stars to be ejected, that stellar ejection can get black holes close enough to merge by gravitational radiation in less than 10 to the 10 years. Okay, now, this is the simplest version. If that was all that was going on, it would mean that almost all of the black holes in the universe should actually be close binary pairs. Remember, almost every galaxy has undergone a merger in the last 10 to the 10 years. That would mean that except for a few special cases, and certainly all of the bigger black holes which dominate the mass, most of them should actually be close binary pairs sitting in the centers of nuclei with separations of the 10th to 100th of a parsec. Okay, so what we thought was actually one black hole producing that rise is actually two black holes orbiting each other. And it's possible that that is true. We actually don't have any very strong observational arguments against that. One possible argument against that is that if you have two black holes orbiting each other like that, if you try to drop gas into them, the same thing tends to happen to the gas as happened to the stars, except of course the gas can have shock waves and cool and so on, but generically it tends to get ejected, and you can think of the two black holes as an egg beater. And if any of you have ever actually done any cooking, you know that if you hold the egg beater kind of sideways in the stuff, you fill up your kitchen rather than. And so this effect in astronomical circles is known as the egg beater, or the propeller effect of putting a propeller into a gas of liquid or stars. And that would make it quite hard for a binary black hole to produce an AGN, because you have to get the gas onto the black hole. So the fact that at least a few % of galaxies show up as AGNs, you now have two possibilities. Either this 4% or the 4% which happen not to be binary black holes, and therefore the accretion can occur. But most people think that this phase actually lasts only of order of 500 million years or so. And so most galaxies have been through this phase. And that would then argue that most galaxies are not actually binary black holes in the centers. But we don't actually have any direct way of testing that, and maybe this egg beater idea is wrong. So people have been driven to consider other ways of trying to get these things to merge, and there's a whole list of possibilities. One effect which I haven't mentioned is that after these two black holes kick all the stars out of the nucleus, they're in quite a flat potential. They're essentially in a vacuum surrounded by stars at larger radii. And so there's not really very much to keep them nailed at the center of that flat potential. It's not very much of a potential well. It's essentially a constant potential in the center. And so every time some little star happens to come in, of course, the star gets ejected at a large velocity, but the center of mass of the binary black hole system gets a little kick and it goes off in some other direction. And then the next one comes in and it goes off. And so gradually you build up a sort of Brownian motion velocity of this center, black hole center of mass. And because there aren't any stars in the center, that velocity can lead to quite large excursions, to excursions of order the size of the region that they've ejected the stars. And that means this loss cone isn't so well defined as you thought, because the black holes keep wandering around, so the direction you have to aim for is a function of time. And that means that they can sample actually a much bigger cone than this naive loss cone where you kept the black holes nailed in the center. So that means there's a larger population of stars available for them to eject. They essentially wander their central position until new stars are aimed at them. Another possibility is that elliptical galaxies are actually triaxial, and there's substantial numbers of stars which are on so-called box orbits. And I sort of described these stars as being on quasi-circular orbits that were never going to get very close to the black hole. And in triaxial systems, those are known as tube orbits and banana orbits and other types. But quite a lot of the stars in a triaxial potential are on so-called box orbits. And those are ones which you can imagine as sort of being a Lissajous figure, where if you sort of make an XY plot of the orbit of the star, it essentially does something like this. And if you wait long enough, it gets arbitrarily close to the center. And the time it takes to get to the center is of order 1 over the ellipticity of the ellipse, of the ellipsoid. So stars on orbits like this could, if you wait long enough, initially be on orbits out here, but you might not have to wait for a two-body encounter to actually scatter it onto a plunging orbit. You could just wait for it to wander in near the center of the black hole. And so there have been calculations of trying to make realistic models of galaxies with elliptical profiles in the outer parts of central black holes to ask what fraction of the orbits to make a self-consistent black hole do you actually need to be box orbits, and how many stars get near the center in the Hubble time. And of course, near the inner parts of the galaxy, the black hole tends to make the potential round, and near the outer parts, it doesn't have much effect. So this is a less strong effect in the inner parts. But again, it looks as if this could be a factor of several improvement. You could perhaps get up to slightly larger mass black holes and substantially elliptical galaxies. And then the third possibility is that real galaxies, in many of the mergers, there's gas that comes in. And the gas in these binary systems, if it comes in, it can keep being ejected and recooling and coming back in again. And so it's possible that you could actually liberate even more. Even if you kicked all the stars out, the next time some gas came in, it might get down in the center and be ejected. So all of those effects lead people to think that probably it's not just these very low mass black holes, but probably a substantial number of the more massive ones actually can get close enough together to merge by gravitational radiation, but we don't have a quantitative theory for exactly how many or how. Okay. So the crucial point is really, I should just say that for typical numbers, the gravitational radiation, you can work out how close two black holes of given mass m have to be for the gravitational radiation timescale to merge them to be less than the Hubble time. And the typical numbers are that gravitational radiation takes over when the separation between the two black holes is less than about the radius where they began to dominate the dynamics divided by 100. Typical number. So for 10 to the 8 solar mass black holes, this number is like a parsec, and this is then about 100th of a parsec. If you 10 to the 16 centimeters is when the gravity wave lifetime becomes less than a Hubble time. These stories I've been telling you, it's quite easy to get to from stellar dynamics without working very hard to get from this R black dot to R black dot over 10 or 20. And so it's the last factor of 5 or 10, which is the issue of all of these subtleties. It's very easy to get down to 10 or 20. But okay. So any questions about the black hole mergers before I start talking about the black holes and the stars?
Do you know about the binary in M31? I mean, there's the supposed binary nucleus there. I mean,
yeah.
Fit into this kind of scenario.
Okay. So that's actually quite an interesting case. Okay. So in the center of M31, and this was first discovered by Martin Schwarzschild by the stratoscope in 1959. He launched this balloon telescope, a sort of precursor of HST. And took a photograph and took the balloon back. And the center of M31 looks sort of like this. It was an ultraviolet telescope. It looks sort of like this. And then, I forget, sometime around 1985, when the first infrared camera for Palomar was built, I suggested to Jeremy Mold that he take a picture with this new camera of M31. And in the infrared, it looks like that. It looked exactly the same as the stratoscope picture. And then 10 years later, HST was launched and fixed, and Todd Lauer took a picture of the center of M31. And it looked like this, because HST had somewhat better resolution, so there was an extra little circle in the middle. So this is UV, this was 2 micron infrared, and this was optical. And then HST took another ultraviolet picture at even shorter wavelength, and that showed this. Okay. Okay, Chandra first thought it saw this, but now it's clear there's an X-ray binary, so let's forget the X-rays. Now, the fact that the UV, the optical, and the infrared all look about the same mean that it's probably not the case that you have a thing like this with some dust in the middle, or dust covering it up, because then it would look very different in the ultraviolet and the infrared, because you'd have much less extinction in the infrared. The other point is that the UV, the far UV, seems to be concentrated just in one nucleus. In this other one, as you look with higher resolution, it actually, this one seems quite centrally concentrated, but this one stays kind of fuzzy. On the other hand, if you take spectra across here, there is absolutely no change in the mix of stars between here and even way out here in the galaxy. In other words, there's no change in the stellar population. It's not that one of these is a blue cluster of recently formed stars. The spectra look absolutely the same, so it's really the same mix. And you can ask, where's the black hole supposed to be? Okay, for a long time, that was not very clear because the optical measurements that were detecting it had spatial resolutions like this. But now we have HST measurements, and we know that the black hole is here. Perhaps actually a little bit off the center, but pretty close to this one. It's not over here, it's not halfway between. And there's still a controversy over what's going on here, but I think one of the most elegant ideas was proposed by Scott Tremaine, and it's not a model, but a statement of what might be happening. And that is that there's a black hole here, and that somehow or other the stars in its neighborhood, and this is all within the region where the black hole should be dominating the dynamics, by the way. Somehow the stars have gotten onto elliptical orbits, and a large fraction of the stars are on ellipses, which are actually not randomly oriented, but all lined up in the same apocentric direction, the same lens vector. And if you have stars on orbits like this, they spend most of their time over here, and therefore make a little bright patch. And you can construct a model where you say that most of the stars are orbiting on orbits like that, and that actually you can make it look very much like the observations. And the question of how all the stars got onto these orbits and how you keep them lined up, because of course there is a background potential, so they'll actually be precessing. It's not an isolated point mass, so the lens vector does precess, and it precesses in about 10 orbits, and 10 orbits is only about 1 million years, so this has to be pretty short-lived, unless there's some effect stabilizing it. But you can also make models of the centers of galaxies, and there are m=1 instabilities where you displace the black hole from the center a little bit. And this is a very extreme m=1 instability, and so it's possible that this is actually spontaneously formed and maintained in that way. But it almost certainly is not two black holes, in the sense this velocity dispersion over here is very low. The internal velocity dispersion is very low. The rise is over here. So it's not two black holes, but it's clearly something quite interesting and weird going on in the stellar dynamics, which is not encapsulated in these standard models. And that might be a warning that perhaps we're missing something. On the other hand, the center of our galaxy is not doing this. So whatever it is, it doesn't happen all the time, because our galaxy definitely is not doing that. Okay, so in the last 5 minutes, let me tell you the story about what happens after this merger, or if there's no merger. Then all we have is we have a black hole with a central star cluster. So we have our central black hole, and we have our little star cluster. And as I said, low mass black holes have steeper star clusters than high mass black holes. And once again, we have exactly the same thing going on as I described for the binary black holes. There will be stars in the neighborhood of the black hole, which are on orbits within the lost cone, which are aimed at the black hole. And after one orbit, those stars will be gone. And then there will be an empty lost cone. And then you have to wait for two-body encounters between other stars, exactly as over there, to scatter the orbits a little bit and scatter them into the lost cone so that they plunge close to the black hole again. Now, stars like the Sun, for these low-mass black holes, million solar mass black holes, stars like the Sun will be tidally disrupted well outside the black hole's horizon. Stars will be shredded. That process is quite interesting, because that means you can work out the rate at which that should happen. The rate of tidal disruption of main sequence stars. And for a galaxy like the Milky Way, it should be roughly once every 10 to the 4 years that a star like the Sun gets tidally disrupted by the black hole in the center of the galaxy. And that then means there's now one solar mass gas disk around the black hole. And the fate of that disk is interesting and complicated, and I won't describe it. Initially, it's a long streamer, and then this precession of the periastron means that the streamer intersects, except if it's a curved black hole, it doesn't intersect the first time, and you have to wait another 100 times till it intersects, and then it heats up and collides, and you have to worry about what fraction of the star is bound, which is about half, and what fraction is unbound, which is about half. The unbound half sails off at 10 to the 4 kilometers a second and might do interesting things to the outer galaxy, and the bound half falls in. But the general consensus is that this should make a flare, which would last about 1 year. And by flare, I mean that this accreting star is brighter than the surrounding galaxy. for a year. So it should be an obvious thing. If you look in the ultraviolet or the X-ray, you should see this bright flash that would last for months to years. And people have been, so that means that if you look at 10 to the 4 galaxies, you should see one a year. And people don't systematically look at 10 to the 4 galaxies well enough, but they look unsystematically at 10 to the 3 galaxies over the past 10 years. And there are 3 or 4 events that look very much like this, where there was nothing in the center of a galaxy, and then 6 months later there was a bright thing, and 6 months later it had gone away. Doesn't look like a supernova. But there's no galaxy that's been monitored where you see the whole history of the flare. So there are candidate events which are interesting, and this seems about right. Now, on the other hand, if this star is a helium star, a white dwarf, a neutron star, or a black hole, especially if it's one of these last two, and kind of marginally if it's one of these two, this star can be swallowed whole by the black hole. Now, if it gets swallowed whole, that's not terribly exciting. It just sort of has some two-body scattering that kicks it into the lost cone, and then it falls in, and that's it. Not much gravitational radiation. On the other hand, if it's scattered onto an orbit that has a parasender somewhere in the range of 5 to 20 GM over c squared, then it turns out that the time scale for gravitational radiation, which is so this is the timescale for gravitational radiation on an orbit, g equals c equals 1 now, whose parasender is this many m, goes as the 4th power, and then there's the square root of 1 minus the initial eccentricity. So this is some number like 0.999 if it's been scattered from large radius, but it only goes as the square root of this. So you can see that as I get closer and closer parasenders, so smaller and smaller angular momenta, slightly smaller lost cone, this gravitational radiation lifetime, even for large eccentricity close to 1, can get very short. Right? And these numbers, sort of this part of the number for a 10 to the 6 solar mass black hole and a 1 to the 10 solar mass object coming in, this number is like a month or so. So the crucial question is whether this timescale for the gravitational energy radiation loss is less than the timescale for scattering out of the lost cone. Okay, so the star has a two-body encounter, which gets it plunging onto this orbit. And now it plunges nearby, loses a bit of energy by gravitational radiation, and comes back out again. And now the question is, will it have another encounter with another star that will kick it onto some orbit that never gets close to the black hole or plunges into the black hole? Or won't it have one, in which case it will go by again and again and again until it gets accreted by the black hole. And so one can calculate the conditions on the parasender and the fraction of stars which will be captured in this way. And you find that indeed it's the total rate will depend a bit on the structure of the cluster and the number of stars as a function of radius. But this capture rate turns out to be essentially similar to this tidal disruption rate. These parasenders are just a little bit larger than the ones that would lead to tidal disruption of ordinary stars. And so the crucial issue is what fraction of the stars are in these compact forms in the center. Now, that depends on so-called mass segregation. And mass segregation happens because this process of dynamical friction is the result of elastic encounters between bodies which would like to get everything moving with the same kinetic energy. And things move, when this object is much heavier that's moving through the star cluster, it's the heavy thing that loses energy because it would have, when it has the same kinetic energy, it would have much lower velocity than the surroundings. But if this object is, that we're moving through is lighter, on average it will gain energy. So what mass segregation tends to do is if I start a population of stars all with the same velocities, the heavy ones will end up with low velocities and the light ones with larger velocities, and the heavy ones will be essentially concentrated. And that time scale for the galactic nuclei is quite short in these inner regions. And so if there are any 5 or 10 solar mass black holes, they will preferentially have been sunk into the region near the central black hole, and they will be captured at quite a high rate. And the best estimates for the rates, some from Mark Freitag, who's sitting over there, is that something like 1 every 10 to the minus 5 to 10 to the minus 7 per year in a galaxy like the Milky Way. Okay.